something electricity plus electronics. So let me start with a very simple and a basic concept that if you have to define voltage exactly, it is a potential difference between two test points, usually measured in volts. Current can be defined as net amount of charge flowing past a specified point during a time interval, usually measured in amperes. And if you want to say what electricity is, it's exactly the aggregate charge flowing in a referred is referred to as electricity. The aggregate charge flow is referred to as electricity. The next important parameter in electricity is power, and it's defined as energy given per unit time or energy consumed per unit time, usually measured in watts. Now, one unit which we frequently come across in our house when we get an electric bill is called electrical energy unit. Let's understand what is that. It's simple. Assume a 60-watt bulb glows for 8 hours and 30 days. That means 1 month. The energy consumed will be how much? How we find it? We multiply 60 by 8. That gives you watt hours. We multiply by 30. That gives me watt hours a day for the 1 month. And if we divide it by 1000, we get 14.4 kilowatt hour for the given load. That means a 60-watt bulb working for 8 hours for the 30 days. So total electrical unit consumed, according to which we get electric bill in a house or in a company or in a college, wherever it is based on how many kilowatt hours you consume. So 14.4 kilowatt hour exactly means 14.4 energy or electrical energy unit. Let's move ahead. When we talk about load and all, actually all those who consumes energy or withdraws current when apply voltage across are known as load. Few examples are fan, bulb, motor, your refrigerator, your air conditioner, your geyser, everything is a load. Let's have some good conductors here. That is your gold, your copper, your silver, your iron, and many more. One of the very nice conductor I prefer is mercury, which is actually liquid and a very good conductor as well. Insulators, examples are bakelite, wood, rubber, varnish. Now, one should know as a human that what is the extent of voltage we can tolerate as a human. So if the DC voltage is 40 volt, as it is a 60 volt. These limits are given, does not mean one should try for it. There's a safer limit given. Then whenever we are working with some, work efficient devices and all, then we have normally what is measured in horsepower, and we should know 1 horsepower is 746 watt. So depending on the number of horsepower, put to multiply with 746 watt, we get in terms of watt. Now the very important part of any electronic or any electrical circuit is the circuit breakers. For example, if there is an excess of current, or there is a short circuit, or there is an overload, in that case, before the load gets destroyed, the circuit should be disconnected. So we have got short circuit protection or overload protection. Some of the examples are fuses, circuit breakers, and many more. The basic idea of what possibly we need in a electronic circuits or electrical circuits. Now, as clear before, if we have to define exactly what is kilowatt hour, or also called as electrical energy unit. Let's take an example. For a TV drawing 360 watt for 2 hours per day, energy consumed by TV per month will be 360 into 2 into 30. What is 360? Its own wattage. What is 2? The number of hours being used, and 30 the number of days in a month. If you multiply, we get this much watt hour. However, units is not in watt hour, it has to be converted to kilowatt hour. So if we divide this by 1000, we get 21 point this, so that is 21.6 unit of electrical energy. There's one example already previously given. It is one more example just to understand it better. Assume the cost of electrical unit in a given area is 15 rupees per unit, then the bill corresponding to this consumption will be 324 rupees. A simple example, probably how you get electric bill at your house. Now let's have some standard things which you're supposed to know, but I have realized that students a lot of confusion in this. First of all, difference between charge of an electron. So one should know either it is charge of an electron or it is charge of a proton. It's this much coulomb. So when we say electron, we have to put a minus sign here, and when we say proton, we have to sign plus sign here. That means minus 1.6 into 10 raised to minus 19 coulomb is the charge of electron, and plus 1.6 is 10 raised to minus 19 coulomb charge of a proton. Simple. They are equal in magnitude but opposite in sign. The 1 coulomb charge consists of how many electrons? The concept is very simple here. Let the number of electrons are n, and charge of 1 electron is 1.6 into 10 raised to minus 19 coulomb. We want to make it 1 coulomb. So n will be nothing but 1 divided by 1.6 into 10 raised to minus 19. If we solve it, it comes out to be 6.25 into 10 raised to 18 electrons. If this much electrons get combined, we get 1 coulomb charge. So it's very obvious that a huge number of electrons has to get collected or has to get combined to make 1 coulomb charge. So it's obvious that 1 coulomb charge is much bigger than charge of an electron. Is it clear? Let's go ahead. The question next is, if you see very carefully, that what are the carriers in a conductor? I need not to tell, when you talk about conductors, it is either electrons or it can be protons, but protons are normally not a conductors, not a carriers. They don't move. So in conductor, purely electrons are the carriers. In semiconductor, we know electrons and holes are the carriers, and one should be very clear in batteries, ions are the carriers. Whatsoever it is the nature of carrier, they all are charged particles. Now let me talk about what is CVS and CCS. This represents actually constant voltage source, which is nothing but a battery having some internal resistance which has to be very low, and a constant current source is having this symbol which provides constant current, supposed to have internal resistance which is supposed to be very high. So here voltage source, this R should be as low as possible, ideally 0, and for current source this should be as high as possible, and ideally it has to be infinity. So you have to remember that the internal resistance has to be very high, the internal resistance has to be very low. Just be sure. This provides constant voltage, this provides constant current. That means this is a 5 ampere current source, it will provide 5 ampere irrespective of any load I connect here. Similarly, there is a voltage source of, assume 10 volts, irrespective of any load I connect here. There is an internal resistance, so it should provide me almost 10 volts every time. That is constant voltage source. Now, one misconception which is always there is, when you ask for the band gap of silicon and germanium, one should know that when we define a semiconductor, actually it has got one valence band, one conduction band, and this is called forbidden band or forbidden gap, and this value exactly decides are you able to transit the electron from valence band to conduction band, because once the electron comes to conduction band, then only there is a conduction. Now this gap is of almost 1.4 electron volt in case of silicon, and almost something 0.6. The values vary from reference to reference, but there's something like this. And when you talk about a barrier potential of a germanium and silicon, then you should know that when a PN junction formation takes place, either in germanium or silicon, a barrier, a potential barrier forms at the junction. You know, something, this will be having a minus, this will be having a plus. So there is a potential barrier, and that potential barrier is order of 0.6 volts in case of silicon, and it is almost 0.3 volts in case of germanium. Normally, our founders don't confuse between the energy gap, the band gap, and the barrier potential. Barrier potential you get only when junction formation takes place. That means when P and N will be forming a junction. You need two types of semiconductors in that. One is N type, one is P type. Whereas for the band gap is concerned, it is immaterial. It is simply silicon semiconductor or germanium semiconductor. Moreover, these units are of energy, that is electron volt, and these units are of volts. I have a very frequent interaction with the student even at MSc level, and they get confused between these two terms which are entirely different. I repeat, this is independent of either PN junction or not. It has to be a semiconductor. Here it has to have a potential difference. So one should be very clear that there should not be any confusion between the band gap and the potential barrier. You must have observed that band gap for silicon is more, potential barrier is more, still it is preferred to germanium. There are its own reasons for it. You have to just see the literature and then find out why silicon is preferred to germanium. Let's see question number 7. Whenever we draw a wave, it is like sine wave like this, then the number of cycles completed per second is known as frequency. Rather, the formula is also 1 upon t. Assume it takes 1 millisecond. So in 1 second it will cover 1000 cycles. So 1000 will be the frequency if time period is 1 millisecond. When I say peak to peak, we have to see that voltage from here to here. This is having a voltage units. When you say amplitude, then this is the value which is called as amplitude. And when we say RMS value, then what the amplitude has to be simply divided by root 2. We get 0.707A, and this is known as RMS value. RMS value is exactly what? If you are running a load with a sine wave of amplitude A, for example 10, and if you divide by root 2, it gives you 7.07. The DC required will be only this much volts, while AC required will be of this much amplitude. So that concept should be very clear. Now when we go to this last sentence, if you see very carefully, there is a word called as reactance and resistance and all. I should be very clear about it that when we talk about resistance, this is the symbol. When you talk about inductor, this is the symbol. When you talk about capacitor, this is the symbol. If any circuit we have got just resistance, when you got a combination of resistance and inductor or resistance and capacitor, then this is known as reactance. In case we have got all the three components in a given circuit, then whatever this fellow offers is called impedance. Basically, unit here is ohm, here is also ohm, here is also ohm. That means resistance unit is ohm, reactance unit is ohm, and impedance unit is ohm. The difference is when it is pure resistor, it is resistance. When it is a combination of resistor or inductor, or a resistor or a capacitor, it is called reactance. And when it is a combination of all the three, In that case, we call it as impedance. Unit remains same. Now the fundamental question here is how you convert DC into AC and AC into DC. The AC into DC, we all know we require a rectifier, and even we know AC to DC to AC we require an inverter. All those whose houses has got an uninterrupted power supply, they know what an inverter is. How many electron flows for 1 ampere? I think you can easily find it. It's Q upon T equal to 1. This Q has to be written N into E upon T equal to 1. N equal to 1. Charge of electron, if I put here, I get 6.25 into 10 raised to 18 electrons should flow per second to give 1 ampere current. Open, short and close I already discussed in detail before. I am not going to talk. Still, if there is a point A and B and there is a gap between them, it's open. If there is a point C and D and there is a resistance between them, that is closed circuit. And if there is a point again A and B, let me take it as, and it is simple joined by a wire, resistance is 0. Here resistance is not 0. Absence of resistance offers infinite resistance. There is a lot of confusion that this is what exactly. Absence of a student from the class is really absent. But absence of a resistance here is actually infinite resistance. There should not be any confusion. For example, if you are using a resistance box, if you put all the keys, actually it is a zero resistance. If you remove infinity, actually it is a open resistance. And if you remove the resistance box itself between two connections and keep the connections open, then again it is an infinite resistance. So if you remove the resistance box but the wire remains open from where the resistance box is removed, the resistance is infinity. The concept should be very clear. Now there is a device called as transformer which looks like something this. It has got a primary turn, secondary turns. If the voltage is, for example, 220, you can make it 22. Then there is a step up transformer where number of turns in secondary are more. This is primary, this is secondary, this is primary, this is secondary. If I assume it is 220, I can make it 2200 volts. Step up, step down. This device specially work on law of electromagnetic induction, and it cannot work with DC because there is no change in electric field and there is no change in magnetic field, so there cannot be induction. So one should be very clear that as far as the transformer is concerned, it cannot work with DC. Now there is a very important and a very interesting exercise which is remaining here. Let me clearly, normally students are very confused about this. So let me see what exactly it is. Assume you are given 6 resistances, each of 12 ohms. You know, how many resistances there are? 6. Each of how much? 12 ohms. What you are supposed to get? You are supposed to get actually the equivalence of 2 ohms, 8 ohms and so on. Let me give a simple example. If you have all the resistances in series, if you have got all the resistance in series like this, see here, 1, 2, 3, 4, 5 and 6. 1, 2, 3, 4, 5 and 6. It is simply 12 into 6, that gives you 72. Here is the answer. Okay. Now it is very obvious, if all you connect in parallel like this will be nothing but 12 divided by 6, that gives you 2. This is the example of 2. Assume you are asked for 8 ohms. Then it is very simple that what you do is you connect one resistance of 12, other resistance 12 in parallel. This becomes 6. You connect one more in parallel. It becomes 4. Then you got a similar combination here. This gives you 12, 12, 12 in parallel, 12, 12 in parallel. This gives you 4. This gives you 4. Total is 8 ohms. Here is the combination. Now what about 18 ohms? Let us see how to get 18 ohms. To get an 18 ohms, you just think over that. One has to be something like this. Just see. 18 ohms means 1 is 12. This gives me 6. This gives me 6. Now let us see what exact is. 1, 2, 3, 4. Actually, we'll have one more resistance here. This parallel gives me 4. This gives me 6. This gives me 12. If you see, total is 22. So this is the resistance here. Right? So the question of series parallel combination. If you practice all this, it becomes automatically very easy and you can do it very nicely. Now the question is of 18 ohms. So what you're supposed to do simply is you connect one resistance and other resistance in parallel. This gives you 6. Have one more resistance and one more resistance. This gives you again 6. Have a similar combination again. This gives me 6. This 6, 6, 6 gives me 18. That's the example here. You are supposed to know how to connect the resistance in series and parallel. I hope the concept is clear. This is a very interesting thing here. The resistances are in series R1, R2, R3. Resistance parallel R1, R2, R3, R4. We know series parallel combination. There's nothing special. But when we see the same thing in terms of load, these bulbs are connected in series and these bulbs are connected in parallel. The interesting part here is if in case if the circuit breaks, then none of the load will be working. Unlike in case if the circuit breaks here, then other loads will be still getting electricity or still working. And in your house, if one bulb goes fuse, remaining load still working. Remaining your fan, your other lights are still working. That is a confirmation that all the loads at your home are connected in parallel. Now there's an important thing here. This type of exercise already discussed before. This I'll prefer to use as a practice exercise, and I think you should be able to do it. Next is understanding circuit in a way. It's a very simple thing here. Nothing very special. If you connect two voltage sources in such a way that positive of one is connected with the negative of other, positive of one is connected with the negative other, then the voltage get add up. So if one is 10, other is 5, it becomes 15. While if you do positive of one with a positive other, the voltage gets subtracted and you get nothing but minus 5, 10 minus 5 and gives you 5 volt. Similarly, if you connect the voltage sources in current sources in parallel, 5 ampere, 5 ampere, the total become 10 amperes. While in voltage sources, if you connect them in parallel, voltage remains same. So see that there is a very nice relation between current and voltage in series and parallel and sources. What way should they be? What way the current sources should be connected to enhance the current? And here we can say what way the voltage sources should be connected to enhance the voltage. I hope I must be understandable. Thank you.